Hi, welcome to StatStuff. I'm Matt Hansen. This lesson is part of an extended series on hypothesis testing in the analyze phase. In this lesson, I'll review the two-variance test, which compares the standard deviation of a continuous value to itself across different time periods, locations, or groups. I'll spend the first part of this lesson reviewing some of the critical concepts that can help you to understand how to use this test. But despite that, I recommend that you at least review the prior lessons on hypothesis testing if you haven't already done so. But for now, let's review again why we even need hypothesis testing.
Well, we need hypothesis testing because, remember, our goal for the project is to resolve the problem by first building a transfer function. We don't want to just alleviate the symptoms that we're seeing, but we want to get to the root cause. You may recall my example of my daughter Hannah. We don't want to just alleviate the arthritis pain that she was feeling in her leg, but we want to heal the root cause, which was the strep throat. So if we don't know what the root cause is, then that means we need to build a transfer function to figure that out. By building the transfer function, we can know what changes, that is, what improvements that we need to make that should fix that root cause. Now, if you recall, the transfer function is defined as y equals f of x. That is, the output response of y is a function of one or more input x's. It's part of the IPO flow model, again, that we described before in the IPO flow model, where we have an input that leads to a process and an output. Well, the y refers to that output. The process piece refers to the function that's applied to an x, the x being the inputs that are part of it. So it's really expressed in the IPO flow model to an equation. Now, how does this transfer function fit with hypothesis testing? Well, hypothesis testing tells us which of those x's, which of those inputs that we're looking at, are independently influencing the y, the output metric. When we reject a null hypothesis, we're building evidence proving which x's are guilty of driving the y. And what we'll do at the end is we'll compile all the evidence in the improve phase of DMAIC, and that's when we'll begin to fix those root causes or come up with a plan that's going to fix those root causes. Now that we know from the hypothesis testing which of the x's are the most critical x's that have the most influence and where we need to make the biggest changes that are going to affect our output y.
Okay, now let's review again the various steps that we follow when doing hypothesis testing.
At a high level, the steps begin with a four-step process, which was starting with a practical problem. We're stating the problem as a yes or no question, and then we want to convert that problem into a statistical problem. That's going to help us to figure out which is the right statistical tool or method we're going to use to help figure out how we're going to do the analysis. And then we apply that statistical tool or concept on it, and then we interpret the results from that and come up with some analytical answer. And then from that, we would interpret the analytical answer into some practical solution or some practical way in applying that so it makes sense to us. And at the heart of doing the hypothesis testing, again, for steps 2 or 3, that's where we drill down to 6 additional sub-processes or sub-steps in order to figure that out. So it started off with defining the objective. Then we want to state the null and the alternative hypotheses. Then we define the confidence level and the power levels based off of the alpha and beta risks that were identified. Collect the sample data, and we want to calculate the p-value. All these are part of building this statistical problem. And then once we've done that and run the test, then we interpret the results. This is going to be the point where we decide whether we're going to accept or reject the null hypothesis. This is what we'd follow when we want to go through the formal hypothesis testing.
All right, now let's review again the chart for finding the right statistical test and where the two-variance test fits into all this.
We'll refer again to the drill down for where we want to find the right statistical test. In this case, we have a continuous value and we want to measure spread or variation from within that continuous value. We find ourselves where we want to compare between two different groups, a one-to-one comparison. This is where we'll find ourselves in this current lesson. We're going to be examining the two-variance test.
Now let's review again the concept of confidence intervals, which is essential for understanding statistical tests like these.
We have to remember the confidence intervals are an estimated upper and lower range of the mean. So the confidence interval will change or become more narrow when you add more samples. So the example we've given before is when we have fewer samples, the population mean falls somewhere within this wide interval. But as we get more samples and distribution grows, the confidence interval represented by these dashed lines gets more narrow. So as we get more and more data that increases, then the confidence interval gets more and more narrow because we could be more confident having more data where the population mean should fall. So we've got to remember that statistics are intended to help us make inferences about a population. So let's say we have a mean of 57 with a 95% confidence interval that falls from 55 to 59. Well, that would imply that although the sample mean is only 57, then we can have 95% confidence the population mean will fall somewhere between 55 and 59. So the more data that we collect, the more narrow this interval becomes. So if we were to double our sample size or triple our sample size, then the confidence interval might narrow. Again, we might come up with the same mean of 57, but it might make it more narrow, where now the range is between 56 and 58. So it gets more and more narrow with the more data that we collect. So the first step that we have in hypothesis testing is to define the objective by asking, is there a difference between something, or whatever it is that we're comparing? Now, the statistical test generally will compare the different confidence intervals between factors to see if that difference actually exists. So an example we've given before is, let's say we only have 20 samples we pulled and we're looking at the difference between factor A and factor B. We might have a mean here at this value for factor A and a mean represented by the dot here for factor B. And the line spread out across each one here between each factor represents the confidence interval. So for factor A, the average actually falls just above 3, maybe like a 3.05 or something like that. And the confidence interval here shows that the population mean actually could fall as low as maybe 2.7, or it could be as high as, in this case, maybe like a 3.3, somewhere within this range, even though the dot represents this is where the mean falls. Well, for factor B, this mean falls at this dot, and that means the population mean can fall somewhere within this range. So you got to remember the tests look for the overlap between the confidence intervals. If there's a lot of overlap between them, then there's a good chance that the actual population mean between the compared factors are possibly the same, or very close to being the same, which is going to result in a higher p-value, a higher level of risk before we can claim any difference. Well, the more samples we collect, then there's going to be more narrow confidence intervals. Having more narrow confidence intervals means there's less of an overlap between them. So that means there's a lot less chance that the population mean is going to fall within the same more narrow spot between both of these compared factors. And as you continue to collect even more data, then as shown here, there's no overlap. And if that becomes the case, then we would say that there is a low or no p-value where we can conclude, yes, there is a statistical difference between these factors after all.
Okay, now let's see how you can run the two variance test in Minitab.
Well, we're going to use this test when we're going to compare two variance values from two random samples across two different normal distributions. So when we want to run the Minitab, then we're going to go to the Stat menu, select Basic Statistics, and choose the two variances test. So what are the inputs that we're going to use for this test? Well, here's what the dialog box would look like from within Minitab. And we're going to select as the sample size collected from each of the groups you're going to be comparing in this first and second group there, it's going to be compared. And then over here in the variance section, you're going to select the variance, not the standard deviation, from each of the samples. It's really important to understand this is not the standard deviation you're going to be typing in, but instead it'll be the variance that you type into these columns. And then you can select the options box. If we're then there, this is where you can select the confidence level that you're going to be using for this particular test.
All right, now let's go through an example of the two variance test.
For this example, we're going to compare the performance between two different call centers. As a background, we'll say we've got each call center that's expected to have a standard deviation of less than 5% for repeat calls from customers. There's a sample of 300 surveys, each from the Phoenix and Reno call centers, to show their standard deviation was 4.8% and 5.2% respectively. Now, for a practical problem, we're asking ourselves, is there a difference in the standard deviation between the two call centers? For a statistical problem for this, again, we're going to state the null and alternative hypotheses, where we'll say the null hypothesis is where the standard deviation for Phoenix is equal to the standard deviation for Reno. And the alternative is that they're not equal to each other. Confidence and power levels will be the same default that we've done before, which is 95% confidence and 90% for the power level. And then the statistical problem that we're going to type in the Minitab, we're going to go to the Stat menu, select Basic Statistics, and choose two variances. We'll select Summarize Data, and then enter in 300 for your sample size for both the first and second, because that's what we said was the number of surveys for each of those different call centers. And we'll also calculate and enter the variance for both call centers. So if you're unfamiliar again with how we calculate the variance, it's simply taking the standard deviation squared. So the variance for one location would be 4.8% times 4.8%. 0.8%, or 0.048 times 0.048. Same thing for the other one, 0.052 times 0.052, or we just square each one of these standard deviations in order to figure out what the variance is that we type into the boxes. And then click the options box and make sure that we have a confidence level of 95% defined in there. This statistical solution that we'll see from Minitab looks like this for the session windows that's created out for Minitab. And from within here, we're going to look again as we do at the p-value, where in this case the p-value is greater than our alpha risk of 5%, and as a result that means we're going to fail to reject the null hypothesis. Or again, the same thing as saying we're going to accept the null hypothesis. We could also get a graph that's generated to illustrate the confidence intervals between each of the different call centers we're comparing. And as you can see, there's a lot of overlap between the two. And because there's a lot of overlap in these confidence intervals, it's probably why the p-value is as high as it is, because we're not as confident that they're distinct between each other, because chances are that for the population, the actual variance between them could end up being about the same. So for the practical solution, we might say the sample that we have is insufficient to prove there's a difference in the standard deviation between these two call centers.
Okay, let's go through another example of the two-variance test.
In this example, we're going to be looking at metric A and category A sample values. So for the background, we're going to use a standard deviation of metric A column that's within the Minitab sample data file that's a part of the website. And we're also going to refer to the category A column of data, but specifically just looking at the two groups for the category of yellow or the category of green, and we'll ignore the other colors that are associated within category A. The practical problem, what we're going to ask ourselves is there a difference in metric A's standard deviation when category A is yellow or green? For the statistical problem, we're going to state the null and alternative hypothesis, where we'll say the standard deviation for yellow is equal to the standard deviation for green, or the alternative is that they are not equal to each other. Confidence and beta values are going to be the same, where 95% is our confidence and 90% is our power level. And then the statistical problem that we're going to type in the Minitab is we're going to first get the volume and the variance for metric A for both yellow and green for category A. It's something already, the category A for that column within the data set has all the other colors, so how do you specifically identify the volume and variance that you're going to be using for just the yellow and green part of category A? Well, the hint that you can use is the graphical summary. You create a graphical summary like we've gone over before in Minitab, and you can specify that you want the graphical summary to be broken out for category A. That means it'll create a graphical summary for each of those different discrete values within category A, yellow and green being among those. So as you look at the results for those discrete values, then you can see within the output for at least the yellow and green category A options, you can see from there the volume within each one as well as the variance or the standard deviation as well. So in Minitab, you go to the Stat menu and select Basic Statistics and choose two variances. And then you select the summarized data and enter the respective sample size and variance that you pulled from the graphical summary for the first and second boxes. And then you click on the Options box and ensure that you have a confidence level of 95%. For solution, the output that's created from Minitab, it's going to look like this, where again we're going to look at the p-value. In this case, the p-value is less than the 0.05 alpha risk that we identified, and as a result, we're going to reject the null hypothesis, which also is the same thing as saying that we're going to accept the alternative hypothesis. And we're going to get another graph that shows up in here as well, and this is where again we're looking at how much overlap there is between the confidence intervals between what's yellow and what's green, and you can see there's not as much overlap between the two. And because there's not as much overlap, there's a 2% chance, which I'm referring to here as the 1.9% that's part of our p-value. There's a 2% chance that the actual variances could fall within this overlapped portion, but that's a very small chance. So the greatest chance is that it's actually going to fall somewhere outside of this, or at least you can say the inverse of the p-value, which is about a 98% confidence it's going to fall outside of this overlapped portion between the confidence intervals of what's yellow and green. So as a result, in how we interpret this practically, we're saying the sample that we have is sufficient to prove that there is a difference in the standard deviation between yellow and green part of category A.
All right, before we close this lesson, let's discuss how we can apply some of these concepts in a practical way.
I'd like you to refer back to the output y and input x's that you identified previously for wanting to run these hypothesis tests. And then for any factor that you've identified that is a continuous value, that's where you want to use that as an example for running through the two variance test. Now, in order to do this, you need to make sure, as we had before, that you're comparing it with at least another discrete value, where you have at least two different sets for the same factor, like it could be across multiple periods of time, different locations, or other different groups or teams, like by state or by country or production lines, or those kinds of things. We're comparing between two different groups. You could also use any other factor that you have in your organization for this exercise if you don't seem to have any of the existing factors you've previously identified that would fit for this scenario. So before you actually run the two variance test, ask yourself, do the standard deviations appear to be different? And then run the test for the two variance test, and then ask yourself, are the standard deviations statistically different between the groups? If the answers for those two questions are different, then ask yourself, how does that affect how you typically measure and communicate the factor from within your organization? So as an example, do the differences between the compared factors somehow affect some financial decisions that are made, or process changes, or maybe other types of critical decisions or actions that are taken within your organization? If it does, then how should the results from this two variance test be used to influence your organization? Should it change how those factors are compared, like across the different times, locations, or the different groups? Or should it change how the factor is being measured? Or should it change how we react when we compare the metric in this way?
Well, that wraps up this lesson. Check out StatStuff.com for many more resources that can help you achieve powerful results. I'm Matt Hansen. Thanks for watching.